Welcome back to the deep dive. Today we are doing something that I honestly think, well, it actually changes the way you see the world.
Totally.
And I don't mean that in a metaphorical, find yourself kind of way. I mean literally. We are looking at the ground beneath your feet. But we're stripping away that mundane idea of just dirt or rock and looking at it for what it actually is.
Which is basically a recording device.
Exactly. A recording device.
I like to tell people that the Earth's crust is essentially a hard drive. It's this massive storage medium. It holds data spanning billions of years,
Right.
recording everything from the temperature of ancient oceans to the atmospheric composition when life first crawled onto land. It's all just sitting there.
And to help us decode this hard drive today, we've pulled together a really serious, kind of eclectic stack of sources. We aren't just skimming basic articles here.
No, definitely not.
We're looking at dense chapters from an introduction to geology, covering all the nitty-gritty of minerals and sedimentary rocks. Plus, we've got technical guides on metamorphic pressure temperature time paths, which is a mouthful, but we will get there.
We will. And to give us that cosmic perspective, because you really can't understand the Earth without looking at space, we are also pulling from NASA technical reports.
Yeah, that conference proceeding, right.
Exactly. The one titled From Stardust to Planetesimals.
Which sounds like the prequel to a sci-fi movie.
It really does.
But it's actually the prequel to us, to the literal ground we stand on. So here is our mission for this deep dive. We are going to trace the entire life cycle of the Earth's crust.
The whole journey.
Right. We're going to figure out how a rock starts as a piece of a dying star, how it gets built into a mountain, how water tries to destroy it, and how it eventually gets completely recycled.
It's the ultimate recycling program. Nothing is wasted. Everything just gets repurposed.
Let's start at the absolute bottom, the foundation. Before we can talk about mountains or canyons or tectonic plates, we have to talk about the bricks.
The atoms.
Yes, the minerals. And I have to say, reading through the source material, I was surprised to find that the definition of a mineral is actually, it's remarkably bureaucratic.
It's very exclusive.
It's like an exclusive club. You can't just be a hard object and get in. There are rules.
Incredibly strict rules. Geologists have a classic definition with 5 very specific criteria.
Yeah.
If you don't meet all 5 of them, you are not a mineral. You are out.
Okay, let's unpack this checklist because there are some really fun loopholes here. Number 1, it has to be naturally occurring.
Right. This is the no humans allowed rule.
Which makes sense.
Yeah. So if you go to a lab and you synthesize a diamond, like you put carbon under immense pressure, and you create a gem that is chemically and physically identical to a diamond dug out of a mine in Botswana to a jeweler, that's a diamond.
Sure, they'll sell it to you as one.
But to a geologist, that is a synthetic simulant.
It's a fake.
It's not a mineral because nature didn't bake it. It has to be a product of natural geologic processes. No factories allowed.
Okay, so that's rule 1. Number 2, inorganic.
Now, this is where it gets tricky. And we actually see some debate in the field about this. Generally, this means the substance cannot be made of complex carbon chains associated with life.
Like proteins and DNA.
Exactly. Sugars, proteins, DNA, those are the domain of biology, not geology.
But the sources brought up a fascinating gray area here. The case of the clamshell.
Ah, yes. The biomineral paradox.
Right, so explain this because I found this wild.
Okay, so picture a clam in the ocean. It's sitting there building its shell out of calcium carbonate, specifically calcite. Now, calcite is definitely a mineral. It is absolutely on the list.
Everybody agrees on calcite.
But because the clam is alive and it's actively secreting this shell using biological processes technically, while the clam is alive, that shell is not considered a mineral by the strictest definition.
Because it's a biological byproduct. It's part of an organism.
Exactly. But the International Mineralogical Association,
Which is basically the Supreme Court of rocks.
it totally is. They had to amend the definition back in 1985 to deal with this. They basically said, okay, we have to draw a line somewhere. Once that clam dies and the shell is buried and it undergoes diagenesis.
Diagenesis being fossilization.
Right, the process of fossilization. Then it becomes a mineral.
So death makes it a mineral.
In the case of biology, yes. Death is the entry fee.
That is surprisingly poetic for a geology textbook. Okay, number 3 on the checklist. Solid at room temperature.
Simple enough. Gases and liquids just don't count. If it's sloshing around, it's not a mineral.
Which brings us to the ice cube debate. This was honestly my favorite part of the intro reading.
It sounds silly, but it tests the definition perfectly.
So if you go to your kitchen, you fill a tray with water and freeze it. Are those ice cubes minerals?
Let's run the list. Is it solid? Yes. Is it inorganic? Yes. Defined chemical composition, H2O, so yes. Crystal structure, yes.
But is it naturally occurring?
No. You made it in your Frigidaire. So a freezer ice cube is not a mineral.
It fails rule 1.
Exactly. However, if you go to Antarctica, or even just look at a frozen puddle in your driveway in January, that ice is naturally occurring.
So glacial ice actually is a mineral.
Absolutely. Glaciers are technically massive metamorphic rocks made of the mineral ice.
That completely blows my mind. I mean, snow is it's just mineral confetti.
Literally falling minerals. Precisely.
Okay, rule number 4. Regular crystal structure.
This one is crucial. The atoms have to be arranged in an orderly, repetitive geometric pattern.
They can't just be a jumbled mess.
Right. If the atoms are just shoved together randomly, like a pile of unwashed laundry, it's not a mineral.
And the text used glass as the counterexample here, which I thought was helpful.
Yeah, think about obsidian, volcanic glass. It forms when lava shoots out of a volcano and cools incredibly fast. It cools so quickly that the atoms inside just don't have time to line up into that nice geometric pattern.
Did you get frozen in place mid-shuffle?
Exactly. Because there is no internal order, obsidian is not a mineral.
So what do they call it then?
It's a mineraloid.
A mineraloid. It sounds like a sci-fi insult. You're nothing but a mineraloid.
It's the almost but not quite category. Opal is in there too.
Oh, really?
Yeah. Opal is beautiful. It looks like a crystal on the outside, but internally, it's amorphous. It's a structural mess.
Wow. Okay, and finally, number 5. A defined chemical composition.
Right. It doesn't have to be completely fixed, but it has to be defined within limits. You need to be able to write a chemical formula for it. So quartz is SiO2. Always.
So if you meet all 5 of those, you're in the club.
You're an official mineral.
And when you get in the club, you can do some amazing things. I have to mention the big wow factor from the reading here. The Cave of the Crystals in Naica, Mexico.
Oh, Nike is just otherworldly. It looks like the Fortress of Solitude from Superman.
But the text said it would kill you in minutes.
Oh, absolutely. The heat and humidity are lethal, but the crystals are unbelievable.
The dimensions mentioned in the text are just insane. Crystals that are 39 feet long, that's 12 meters, weighing 55 tons.
Imagine a single continuous crystal the size of a school bus.
How is that even possible?
Well, these are selenite crystals, which is a form of gypsum.
How does nature build something that precise on that massive of a scale?
It's basically a masterclass in stability. This cave sits above a magma chamber, but not too close. For hundreds of thousands of years, the cave was flooded with mineral-rich water that stayed at a perfectly stable temperature.
Like exactly stable.
About 58 degrees Celsius? Constantly.
So it was just a giant hot bath.
A very consistent hot bath, and because the temperature never fluctuated, the atoms could just keep stacking and stacking onto the crystal lattice without any interruption for millennia. Usually the Earth is messy. Temperatures change, water drains away, things shift. Naica was just a fluke of perfect, undisturbed stability.
It's amazing what time and stillness can do. But I want to zoom in now. We've talked about these school bus-sized crystals, but to really understand what's happening, we have to look at the atomic architecture. The source material goes into the chemistry a bit here, specifically about the atom itself.
You really can't understand minerals without understanding the atom. At the most basic level, we have the nucleus, that's your protons and neutrons, and then there's this buzzing cloud of electrons on the outside.
And the text specifically mentions isotopes.
Yes, this is crucial for the historian aspect of rocks that we're going to get to later. An element is defined by its protons. Carbon always has 6 protons. If it has 7, it's nitrogen. But the number of neutrons can vary.
Right.
So you can have carbon-12, which has 6 neutrons, or carbon-14, which has 8.
And carbon-14 is the heavy one.
It's heavy and it's unstable. It's radioactive. It essentially wants to fall apart. And because it falls apart at a very specific measurable rate, it acts like a clock. That is exactly how we date things.
But for holding the rock together in the first place is all about the bonding. The text distinguished between ionic and covalent bonding. I really like the way they describe ionic bonding as being greedy.
It is a totally transactional relationship. Think of table salt. Halide. You have sodium and chlorine. Sodium has 1 extra electron it desperately wants to get rid of to become stable. Chlorine is desperate to get 1 extra electron.
So sodium just shoves it over to chlorine.
Exactly.
Yeah.
Sodium gives it up. And now, because electrons are negative, sodium becomes positively charged and chlorine becomes negatively charged.
And now they are magnetically attracted to each other.
Right. Zap. They stick together. Positive and negative. But, and this is key, it's a relatively weak bond. That is why salt dissolves so easily in water. The water molecules can easily pry those ionic magnets apart.
Contract that with covalent bonding.
Covalent is more like a solid marriage. The atoms share the electrons. They actually merge their electron clouds. This is what you see in diamonds. Carbon atoms sharing electrons in this tight 3D network. That sharing is incredibly strong.
Which is why you can't dissolve a diamond in a glass of water.
Thankfully, no. And it's why diamond is the hardest natural substance.
Okay, so we have atoms bonding to make minerals. But looking at the Earth's crust as a whole, it seems like there's one power couple that just dominates everything. The text calls it the Silicon Empire.
It really is a staggering monopoly. If you scooped up a random bucket of the Earth's crust and separated all the elements by weight, oxygen makes up 47%. Silicon makes up 28%.
So 75% of the literal ground is just those two things.
Basically, yes, 3/4 of the crust, which means the vast, vast majority of minerals out there are just different ways of arranging silicon and oxygen. We call this entire group the silicates.
And they build a very specific geometric shape, the silicon-oxygen tetrahedron.
I love this visual. It's a pyramid, a four-sided pyramid. You have one tiny silicon atom tucked in the middle, surrounded by 4 big oxygen atoms at the corners. This structure is the ultimate Lego brick of geology.
The fundamental unit.
Everything in the silicate world depends on how you stack these pyramids. If you understand the stacking, you understand the rocks.
Let's walk through these Legos of geology, as the text called them. Because it starts simple and gets incredibly complex. It starts with independent tetrahedra.
Right. Imagine you have a bag of these pyramids, but they aren't touching each other. They don't share any oxygen atoms. Instead, they are held together by other glue atoms floating around, usually iron or magnesium. This specific arrangement gives us the olivine family.
Olivine. That's the green one, right?
Yes, olive green, hence the name. It's very rich in magnesium and iron. We call that mafic. It's heavy, it's dark, and it typically forms deep down in the mantle.
Okay, then we start actually linking the pyramids together, the single chains.
Now, the pyramids are holding hands in a long line. They're sharing oxygen atoms. This creates the pyroxene family. Augite is a common one. These are usually dark, black, or green rocks.
Then we get to double chains.
The amphibole family. Hornblende is the famous one here. You're just sticking 2 single chains together side by side. The structure is getting more complex, more rigid.
And then sheets. This one made the most intuitive sense to me because of the sandwich analogy the text used. The micas.
Oh, the micas are great. Biotite and muscovite. If you have ever held a piece of mica out in the woods, you know you can just peel it apart in these incredibly thin, transparent layers.
It flakes off like pages in a book.
Exactly. And that happens because the silica pyramids are arranged in flat, 2-dimensional sheets. The chemical bonds within the sheet itself are really strong. That's the bread of the sandwich.
Right.
But the bonds between the stacked sheets, the sandwich filling, are these incredibly weak forces called van der Waals bonds.
So when I peel a piece of mica, I'm literally just breaking the filling.
You're ripping the sandwich apart at its weakest point.
That's a great way to picture it. And finally, the ultimate structure, the frameworks.
The heavy hitters. Quartz and feldspar. Here, the pyramids are interlocked in a complete 3D network. Every single oxygen atom is shared between 2 silicon atoms. It makes them very strong and very, very common.
Because it's a super stable structure.
Highly stable. Feldspar is actually the single most abundant mineral in the entire Earth's crust. If you go out and pick up a random rock in your backyard, it is almost certainly mostly feldspar.
So that covers the massive Silicon Empire. But the text lists some non-silicates that honestly seem pretty important for human civilization.
Absolutely vital. These are the salts and the ores. You have the carbonates, like calcite. That's what makes up limestone. The key field identifier there is that they fizz if you drop acid on them.
Which is why every field geologist carries a little dropper bottle of hydrochloric acid.
Standard issue equipment. You just put a drop on the rock, and if it bubbles, you know you've got carbonate. Then you have the halides. That's your table salt, halite, and things like sylvite. They usually form when ancient seas evaporate.
Leaving all the salt behind.
Right. Then we have the native elements. These are the pure metals floating around unbonded. Pure gold, silver, copper.
And finally, the sulfides.
Yes. This is where we get a lot of our industrial metals. Galena gives us lead. Sphalerite gives us zinc. And then there's pyrite.
Fool's gold.
Fool's gold. Iron sulfide. It looks exactly like gold to the untrained eye, but there's a trick. If you scratch it on a piece of unglazed white porcelain, a ceramic plate, the powder streak it leaves behind is black.
Really? Black?
Yep. Real gold streak is actually gold-colored. That's the quickest way a prospector can tell if they've struck it rich or if they're holding iron sulfide.
Okay, so we have identified the building blocks. We know what minerals are and how they're structured.
Yeah.
But I want to pivot to where they actually come from.
Mm.
And I don't mean, they come from the volcano. I mean where they really come from.
The deep cosmic origin.
Yes. We looked at those NASA technical reports. The conference was called From Stardust to Planetesimals. And this just puts a whole new spin on holding a rock.
It really does. It takes standard geology and turns it into astronomy. The core concept here is that the minerals we see today, or at least the raw chemical materials for them, have origins that significantly predate our solar system.
Stardust, which sounds like a poetic, metaphorical term.
But it's not. It is a literal technical classification. We find these microscopic grains called presolar grains trapped inside meteorites.
So they're older than the sun.
Yes. These are microscopic bits of diamond, graphite, or silicon carbide that actually formed in the expanding, cooling atmospheres of dying stars or in the violent explosions of supernovae billions and billions of years ago.
So when I hold a meteorite at a museum, or even just look at the dust settling on my shelf, some tiny fraction of that might be literally older than the sun itself.
Absolutely. The NASA reports talk about how we study this today using infrared spectroscopy. We can point telescopes at distant galaxies and actually see the spectral signature of this dust floating in deep space. We know what kind of minerals are out there between the stars because the light signatures match exactly what we find inside meteorites that crash to Earth.
And the process described in the papers is this slow aggregation, right? It all starts as dust.
Stardust, basically the dust bunnies of the universe. In the early solar nebula, before the sun even fully ignited, these tiny grains start to stick together.
Gravity.
Actually, no, not at first. They're too small for gravity to do much. It's electrostatic forces. Static cling, just like a balloon sticking to your hair. It pulls these microscopic grains together.
And dust to pebbles.
From pebbles to boulders, and eventually, from boulders to planetesimals. These are city-sized or moon-sized rocks. And the report specifically mentions the Kuiper Belt way out past Pluto as a key piece of evidence for this whole process.
Why the Kuiper Belt? What's out there?
It's essentially a deep freeze. It contains planetesimals that never got mashed together to form a full planet. They are pristine, untouched relics.
They're the leftovers.
Exactly. They're the leftover bricks from the construction site of the early solar system. By studying them either with probes or by analyzing the ones that get knocked out of orbit and fall to Earth as comets or meteorites, we are looking at the raw, unbaked ingredients of Earth.
So Earth eventually formed from these planetesimals smashing together, generating massive heat, melting, and differentiating into a core, mantle, and crust. We got our crust, we got our minerals, but the story doesn't stop there. Because once a rock is formed and sitting on the surface of the Earth, it is immediately under attack.
Enter the destroyer.
Right. Section 4 of our outline deals entirely with weathering. And the biggest weapon in nature's arsenal against solid rock seems to be water.
Water is so deceptively powerful. We always think of it as soft, gentle, life-giving. But chemically and physically speaking, water is a sledgehammer.
The text highlights the polarity of the water molecule as its main weapon.
This is its absolute secret weapon. A water molecule is shaped kind of like a Mickey Mouse head. The big oxygen atom is the face, and it carries a slight negative charge. The two little hydrogen atoms are the ears, and they carry a slight positive charge.
So it acts like a little magnet or a battery.
Exactly. It has poles, and that polarity allows it to literally rip other things apart.
It pries ions away from the crystal lattice.
We call water the universal solvent. Given enough time, water can dissolve almost anything because those little positive and negative ends are constantly tugging at the atoms in a mineral, trying to pull them away.
And then, beyond the chemistry, there's the sheer physical violence of water. Mechanical weathering, and specifically frost wedging.
Frost wedging exploits a very weird quirk of physics. Most things in the universe get denser and shrink when they freeze. Water is one of the very few substances that actually gets larger. It expands by about 9% when it turns into ice.
So if liquid water seeps into a tiny crack in a rock,
and then the temperature drops and it freezes, it pushes outward with thousands of pounds of pressure per square inch. It acts like a hydraulic wedge. It can split a massive solid granite boulder perfectly in half over time.
that is why we have so many potholes in the spring, right?
Exactly the same principle. Water gets under the asphalt, freezes, expands, and shatters the road. It's also why alpine mountains look so jagged and sharp. They're constantly being shattered by ice freezing and thawing day in and day out.
And the text also mentioned root wedging, which is just trees doing the same thing, prying rocks apart as their roots grow. But then there's exfoliation. This one sounded almost like the rock is relaxing.
I love exfoliation. So
Right.
imagine a massive blob of granite forming 5 miles underground. Because it's so deep, it is under immense crushing pressure from the millions of tons of rock sitting directly on top of it. It's hypercompressed.
Okay.
Then, over millions of years, erosion slowly removes all that top layer of rock.
We call that unroofing, right?
Yes, unroofing. Suddenly, the confining weight is completely gone. The granite expands outward. It literally heaves a sigh of relief. And as it expands, the outer layers crack and flake off in these massive curved sheets, almost like layers of an onion peeling off.
It's incredible.
If you've ever seen Half Dome in Yosemite National Park, you know that huge, smooth, curved face. That is textbook exfoliation. The mountain is expanding and shedding its skin.
So that covers mechanical weathering, just breaking big rocks into smaller rocks.
Right.
But then comes chemical weathering, the acid attack.
This is where the actual chemistry of the rock changes. It doesn't just break, it rots.
And there was a math concept here that I thought was brilliant, the surface area to volume ratio. The text used a cube as an example.
Oh, it is the absolute perfect illustration of why mechanical weathering and chemical weathering work together. Imagine a solid cube of rock, exactly 1 meter on each side. Chemical weathering things like acid rain or oxygen can only attack the exposed outer surface. The middle of the block is perfectly safe.
Right.
Now, take a hammer and break that cube into fine dust. You haven't changed the total volume of rock. The amount of stuff is exactly the same, but you have massively, massively increased the surface area exposed to the air and water. You've gone from 6 square meters of surface area to literally millions of square meters.
So mechanical weathering basically speeds up chemical weathering.
Exponentially. By breaking the rock apart, mechanical weathering opens a million tiny doors for the chemistry to get in and do its destructive work.
Let's look at those chemical weapons. The first big one is hydrolysis.
This is the process that destroys feldspar. And remember, feldspar is the single most common mineral in the crust. Water chemically reacts with the feldspar crystals and alters their structure, turning them into clay.
Just normal clay.
Yes. This is literally how majestic, solid granite mountains eventually turn into soft, squishy mud. The hard crystals are chemically transformed into clay minerals.
And then there's dissolution, which is water, especially slightly acidic water, just dissolving rock completely, right?
Yes, mostly limestone. It creates karst topography. That's how you get massive underground cave systems and sinkholes. The rock just vanishes into the water.
And oxidation.
Rust, plain and simple.
Right.
If a rock has iron in it, like olivine or pyroxene, the oxygen in the air and water reacts with it to form new minerals like hematite or limonite.
Which are rust.
Right. This is exactly why the Grand Canyon is red. It's why Mars is the red planet. The rocks are literally rusting away.
Now, the text introduced a concept near the end of this section called Goldich's dissolution series. And this felt like a really big aha moment for me in understanding how landscapes actually work.
It's brilliant because it connects everything right back to the beginning. Remember, we talked about olivine forming deep down in the mantle at incredibly high temperatures and pressures.
The green independent tetrahedra.
Right. Well, Goldich observed a very consistent pattern. The minerals that form at the highest temperatures and the highest pressures, like olivine, are the absolute most unstable when they are exposed at the surface. They rot the fastest.
Why is that? Why do the tough, deep earth minerals break down so easily?
Because they are the furthest away from their home environment. They are the ultimate fish out of water. The surface of the earth is cold, it is oxygen-rich, it is wet, and it is at low pressure. Olivine absolutely hates it here. It's entirely out of equilibrium, so it breaks down chemically almost immediately.
But what about something like quartz?
Quartz forms at much lower temperatures, very late in the magma cooling process. The conditions where it forms are much closer to surface conditions. So when quartz finally gets exposed at the surface, it is relatively stable. It's just chill.
And that is why beaches are made of quartz sand.
Exactly. The beach is the graveyard of the durable.
I love that.
All the olivine, all the pyroxene, the feldspar, they all rotted away to clay and washed out to the ocean. The quartz is the only thing tough enough, the only thing chemically stable enough to survive the whole journey down the river to the sea and then survive getting battered by waves.
That is a profound thought next time you're walking on the beach. You're walking on the lone survivors. Okay, so we have weathered the rock. We have broken it down into clay and quartz sand. Now we move to section 5. The historian, Sedimentary rocks.
This is where the planetary hard drive actually starts recording the data.
The process described is lithification, which just means turning loose dirt back into solid stone.
Right, and it happens in two main steps. First is compaction. As sediment piles up, the sheer weight of the dirt on top squeezes the stuff at the bottom. It squeezes all the water out of the pore spaces.
And the second step.
Cementation. It's gluing it all back together. Usually, mineral-rich groundwater slowly flows through whatever tiny pores are left and precipitates minerals, usually calcite or silica, that act like a natural cement, binding the grains together.
And the sources say we broadly classify these sedimentary rocks by what they're actually made of. The first type is clastic rocks.
Also called detrital. These are rock made entirely of broken pieces of other rocks, just fragments glued together.
And here's where the real detective work begins. The sources talked about looking at grain size using the Wentworth scale.
Yes. From boulders to cobbles, down to sand, silt, and finally clay. The size tells you about the energy of the environment. A fast-moving mountain stream can move boulders. A slow, lazy swamp can only move tiny clay particles.
And we also look at sorting.
Sorting is fascinating. It tells you how picky the transport mechanism was.
Picky.
Yeah. Wind, for example, is incredibly picky. It only has enough energy to carry sand of a very specific uniform size. It leaves the heavy rocks behind, and it blows the fine dust far away. So a sand dune eventually becomes a well-sorted sandstone. Every grain is the exact same size.
What about a glacier?
A glacier is the exact opposite. A glacier is a giant icy bulldozer. It does not care. It pushes everything. Mud, sand, gravel, house-sized boulders. So glacial deposits are totally poorly sorted. It's a jumbled mess. Just by looking at the sorting of the rock, you know immediately if it was deposited by wind or by ice.
And the third detective clue was rounding.
Rounding tells you about travel distance. If a grain of sand is jagged and angular under a microscope, it hasn't traveled far from its source. It's fresh off the mountain.
It hasn't been beaten up yet.
Exactly. But if it is perfectly round and smooth, it has been tumbling in a river, smashing against other rocks, or rolling back and forth on a beach for a very long time. The corners got sanded off.
So that covers the clastic rocks. But the text also detailed chemical rocks.
These are formed by precipitation out of water rather than gluing broken pieces together. You have evaporites. Think of the Bonneville salt flats in Utah. The water evaporates and leaves the dissolved minerals behind. And they actually precipitate out in a very specific order. First calcite, then gypsum, and finally halite.
And biological chemical rocks.
Yeah. Right, like limestone from ancient coral reefs or chalk, which is made of billions of microscopic shells.
But the absolute coolest part of sedimentary rocks, for me, was the section on sedimentary structures. The text called it Reading the Diaries of Rocks. Let's start with ripples.
Ripples are amazing physical snapshots of a single moment in time. If you find fossilized ripples in a piece of sandstone, you look closely at their shape. Are they perfectly symmetrical, like little repeating peaks?
Symmetrical means waves.
Yes. It means water was washing back and forth equally in both directions, like on a beach. But if they are asymmetrical, meaning they are steep on one side and shallow on the other.
That means a current.
A current flowing continuously in one direction, a river or wind-blowing sand dunes, we can actually measure the slope of those fossilized ripples and tell you exactly which way the wind was blowing 200 million years ago.
That's just wild. And mud cracks.
Mud cracks are proof that an environment was wet, like a tidal flat or a shallow lake bed. And then the water retreated and it completely dried out under the sun, causing the mud to shrink and crack before it got buried.
And then there were geopedal structures. The text affectionately called these up indicators.
This is a vital concept in field geology because tectonic forces, continental drift, mountain building, they can fold and flip entire rock layers completely upside down. Imagine a massive car crash where the cars flip over. Continents do that to massive beds of rock.
So we need to know which way was originally up to read the layers in chronological order.
Exactly. If the book is upside down, the story makes no sense. So we use gravity. One great up indicator is graded bedding. In an underwater landslide or a flood, all the material gets suspended in the water. As it settles, gravity takes over. The heaviest, largest rocks settle to the bottom first, then the sand, then the silt, and finally the fine mud on top.
So the big grain should always be at the bottom.
Right. If you walk up to a cliff face and you see the big cobbles are on the top of the layer and the fine mud is on the bottom,
you know the world is completely upside down.
the tectonic plates flipped that entire mountain over. You can also use footprints. If a dinosaur footprint is pressed down into the rock, you are looking at the original top surface. If it's a raised cast sticking out towards you, You're actually looking at the bottom of the mud layer that eventually filled the footprint in.
Incredible. So sedimentary rocks perfectly record the surface conditions,
Mm-hmm.
but rocks don't just stay neatly layered on the surface forever. They get buried. They get pushed deep down into the crust. And that brings us to section 6, the traveler, metamorphic PTT paths.
Now we are going deep. PTT, pressure, temperature, time.
The source in the Science Education Resource Center, SERC, emphasizes that metamorphism is highly dynamic. It's not just putting a rock in an oven and cooking it. It's a physical journey through the Earth.
Think of it as a graph. The bottom horizontal axis is temperature, increasing to the right. The vertical axis is pressure, or depth, increasing downwards. As a rock gets buried by tectonic forces, it gets hotter and it gets squeezed harder. If we plot its changing conditions on that graph over millions of years, we trace a line.
That line is the PT path.
That is the path, and there are two main legs to any rock's journey.
Right. Prograde and retrograde.
Prograde is the heating up and going deeper phase. This is the rocky descent into the crust. Retrograde is the cooling down phase, as tectonic forces push the rock back up towards the surface. We call that exhumation.
And the specific shape of this path, the loop it makes on the graph, tells us the tectonic story of that region. The text specifically contrasted clockwise versus counterclockwise loops.
This is where we get into high-level geologic forensics. A clockwise path on the graph usually indicates a massive continental collision. Think of the Himalayas forming when India smashed into Asia.
Okay, so what happens to the rock there?
In a collision, the crust is thickened rapidly. Rock is shoved deep underground very quickly, so the pressure goes up extremely fast. But rocks are terrible conductors of heat. It takes a long time for them to warm up. So on the graph, the path spikes downward high pressure before it moves to the right to heat up.
So pressure leads temperature in a collision.
Exactly. It's buried cold, then slowly bakes. But a counterclockwise path, that indicates the opposite. That usually happens in an area where you have a massive influx of magma from the mantle, heating things up dramatically before the rock is fully buried.
The heat arrives before the pressure.
Right. Temperature leads pressure.
But here is the question that kept nagging me while I read this section. How do we actually know? The rock doesn't have a GPS tracker attached to it. It doesn't keep a written diary.
It actually does. It really does. It has something called mineral memory.
Okay, you have to explain that.
Let's look at a garnet. Garnets are very common metamorphic minerals. As a garnet crystal grows in a solid piece of rock deep underground, it grows from the inside out. Very similar to the rings of a tree.
Okay, I can picture that.
The very center core of the garnet formed when the rock was at one specific depth and temperature, let's say 10 kilometers down. As tectonic forces push the rock deeper, down to 20 kilometers, the pressure increases. The garnet continues to grow, adding a brand new layer around the core.
And the chemistry of that new layer reflects the new pressure.
Yes. The chemical composition of that new outer layer is slightly different because the pressure and temperature conditions were different when it crystallized.
The text called this zoning.
Chemical zoning. We can take that rock back to the lab, slice the garnet crystal straight down the middle, and analyze the chemistry from the core all the way to the rim with a laser. By looking at how the chemistry changes layer by layer, we can mathematically reconstruct the entire travel itinerary of that rock through the Earth's crust.
The garnet literally is the flight recorder.
It is the black box of the crust.
That is absolutely unbelievable. And the text also mentioned reaction textures as another clue.
This is evidence of a rush job. It's when things change too fast. Sometimes you find minerals that are completely out of chemical equilibrium. The text mentioned andalusite and sillimanite.
Right.
These are two minerals made of the exact same chemical ingredients, but their atoms are arranged differently because they prefer different pressure conditions. Under normal, slow circumstances, they really shouldn't exist together in the same rock. One should fully convert into the other.
But if we find them actually touching each other in a single rock sample...
If they are touching, it tells geologists that the tectonic changes, the uplift or the burial happened so incredibly fast that the rock just literally didn't have enough time to finish the chemical reaction. Yeah. It's a frozen snapshot of a highly chaotic, violent geological moment.
So we have traced this entire journey. Now let's try to synthesize this for the listener because we've covered billions of years of history in about an hour.
Let's connect all the dots.
We started with stardust, literal microscopic grains forged in dying stars, floating in the cold vacuum of space.
They clumped together via static cling to form planetesimals in the early solar system.
And those planetesimals violently smashed together to build the Earth. And deep inside, the atoms sorted themselves out, silicon and oxygen taking charge, bonding covalently to build those tetrahedra pyramids.
Those mineral pyramids locked together to form massive igneous rocks. But then the destroyer arrived on the surface, water. It froze in the cracks and shattered the granite. It dissolved the feldspar, turning it to clay. It rusted the iron.
It turned these majestic towering mountains into nothing but clay and sand.
That loose sediment was washed down rivers to the sea, sorted perfectly by the wind and the waves, and eventually buried under its own weight.
Where it lithified back into solid stone, recording the asymmetrical ripples of some ancient, long-gone tide.
And then plate tectonics took the wheel. That sedimentary rock was dragged deep down into a subduction zone. It was squeezed, it was cooked, it traced a massive PTT path deep into the crust, growing zoned garnets that recorded every pound of pressure along the way.
And finally, it was exhumed, pushed all the way back up to the surface for us to just stumble upon on a hike.
It is a continuous, relentless cycle of creation, destruction, and recycling on a planetary scale.
You know, there was one thought from the very end of the outline that really stuck with me. The concept of the destruction layer.
Ah, yes. This circles right back to Golddich's dissolution series.
Right. If the minerals that are formed deep underground are inherently unstable when exposed at the surface, that means the surface of the Earth, the place where we live and thrive, is actually a highly hostile environment for the Earth's interior building blocks.
That is such a fascinating way to frame it. We as humans usually think of the deep earth as hellish, right? Magma, crushing pressure, heat. But to an olivine crystal, the surface is hell. The surface is full of highly corrosive oxygen and acid rain. We live on the very boundary layer where the planet is constantly falling apart.
We live in the recycling bin.
We do. And this is the really vital part, to remember that destruction is exactly what makes our biological life possible. Without the chemical weathering of rocks, we wouldn't have soil. The plants need those released ions. Without soil, we have no agriculture, no civilization. We literally exist because the rocks are rotting beneath our feet.
So, what does this all mean for the listener? How do we walk away from this?
I think it means that you should never, ever look at a rock the same way again. It's not just a rock, it's a highly detailed document.
I really want to encourage everyone listening. The next time you go outside, pick up a rock.
Mm.
Any rock at all. Don't just kick it down the street.
Actually look at it. Ask it questions. Ask it, what is your PTT path?
Were you part of a colossal mountain range that doesn't even exist anymore? Were you a grain of sand on a beach 300 million years ago? Are you actively rusting right now?
Where have you been? And where are you going next in the cycle?
It really does turn a simple walk in the park into a walk through a library of billions of years of history. Thanks for joining us on this deep dive into the ground beneath our feet.
Keep looking down. You really never know what you might find.
See you next time.